Alright, so today I'm going to explain special relativity, or specifically the invariance of the interval. Now, for this explanation, I'm going to be using two types of inertial reference frames. Now, the first one is going to be called the laboratory frame, or essentially, if you want to call it, the frame that will not move. So, I'll just draw that, represent it with, kind of a cubic space. Now remember, this cube is expanding infinitely in all sorts of directions. And in this cube, we're measuring it through, multiple points set up in, reasonable distances that are all uniform from each other. This is an inertial reference frame, and in it we'll have objects, moving, and we use it so we can measure them. So this is going to be the laboratory frame, or L. It's not going to move. But now we also are going to have something called a rocket frame. Now, the rocket frame is essentially a representation of the fact that this frame will be moving in essentially one direction. So, this is the rocket frame. Let me just get that right. And now the rocket frame and the laboratory frame are both working on the same axis here. They're both aligned by the same, kind of axis here. So, that means that the rocket frame, in the way that it moves, will be in x. So we just draw that arrow, and this will move in the x direction. Now, the rocket frame will always be on the same y level with the laboratory frame, because inherently, since it's only moving in the x direction, that is its only rate of change. So when we start the rocket frame on top of the laboratory frame, which we will be doing, they will not move from their y-coordinates. The y-coordinate of the laboratory frame, or y, will always equal y prime of the rocket frame. Alright, so now we're going to move on to the invariance of the interval. And for that, I have a specific situation. So now we have a point in space, and from this point will be the origin of both the rocket frame and the laboratory frame. We're starting the rocket frame and the laboratory frame right on top of each other, so all of their coordinates individually match up. All regular digits equal all prime digits. So now from this point, at this point in time and space, is going to be released a flash of light. And so we have, a flash. And this flash will essentially be received on a reflector on the rocket frame, which will be starting at one point of y value above it. So we're going to write this as small r. Now r is going to move, since we're doing this first in reference to the laboratory frame. Now once that flash of light moves, everything starts getting going. The reflector, since the rocket is moving in the x direction, is going to move to about delta x difference, or rather delta x over 2, distance in space. And now the reflector is here. And so the flash of light, when it reaches the reflector, has traveled yay amount of distance. And then the reflector reflects that flash of light back to a receptor on the laboratory frame. So as you can see, this has created a sort of a triangle here. And the triangle can be split into two right triangles. That's marker. Right. Two right triangles. Now, the reflector, as we said in the beginning, starts at 1 y above the, 1 in terms of y, above the origin. So this here is going to be 1. Now, the hypotenuse of the triangle is essentially how long in light time it took for the flash of light to hit the reflector, since the reflector moved from here to here. So now this is going to be delta t over 2. And the reason that it's delta, I'm sorry, that isn't very well written, but the reason that this side here is delta t over 2 is because delta t is the entire amount of time that it took for light to transverse space-time to get from the origin to the reception, or emission to reception if you prefer. So now, as you can see, we have a right triangle, or rather two right triangles. So since, the magnitude is going to be multiplied by 2, so we have 1, and so now we have delta x squared plus the interval squared times 2. So, 2 of 1 squared equals delta t. And now if we put this out into an equation where we have variables on one side and constants on the other side, we get delta t squared minus delta x squared equals 1. Or rather 2. 2 times 1, so that's 2. So that 2 is the distance here, or as we're going to call it later, the interval. And now we're going to see another instance in which something similar to this will occur. So now we have another frame. I'm going to leave the laboratory frame up there for reference. We have another frame, and this time, from here, we were measuring things in terms of the laboratory frame. We were just using a rocket frame to move the mirror, and essentially show that when the rocket frame is moved relative to the light flash, it will come back, and the difference will be delta x. Delta x is the total x that is traversed, and delta t is the amount of time that took together. But now we're going to look at what happens if we were to use the rocket frame as a reference. Now, the reason that we call them inertial reference frames is because in that inertial reference frame, when it's moving, the particles inside of it will still act as if it weren't. So, even though everything in the next demonstration I'll be showing will be moving in reference, relative to the laboratory frame, everything inside will not. So, inherently, that means that we have an event that happens here at the origin, or point of emission, and that will go, as we know, to the r, which is 1 coordinate of y above the origin, and it's going to go 1 up to it, and then right back. And see, that's because in this frame, both the reflector and the origin were moving, and they're moving at the same pace, so everything that happens to them essentially cancels out, and light just goes right up and right back. So since they just came right up and right back, delta x will be equal to delta x prime. Will be equal to 0. Delta t, and since we have our equation for what happens, we have delta t squared plus delta x squared prime equals 2. Essentially the entire distance of the light had to traverse. So now we do this, and we are going to take this and essentially say that delta x, as you can see, is 0. So that's going to go away. So we have delta t prime squared equals 2. So that means that the light here traversed a total distance of 2 meters worth of light time. So now we come to the issue. Both delta t prime squared minus, that's going to be actually minus up here, I'm sorry. Delta t prime minus delta x prime squared equals 2. And delta t from our earlier laboratory investigation squared minus delta x squared equals 2. They both equal 2. We can put this into the same equation, which is going to be delta t squared minus delta x squared equals delta t prime squared minus delta x prime squared. And so, as we can see, from the rocket explanation and the laboratory explanation, the one thing that hasn't changed is the value of this, the interval between the reflector and the origin. So, essentially the altitude of these right triangles has not changed. And that is the unifying component in these reference frames that make it the invariance of the interval. The one coordinate, the one component that will allow us to essentially make them relevant to each other, to use them in calculations. So, that is the invariance of the interval. Thank you, Miguel O'Malley.